I don't know how to do yet.
Right.
So I sat there and I was like,
Well, sometimes you have those things. All right. It's a time for your brain to refresh, relax.
It's also that weird period before Thanksgiving break.
I know it's always weird around Thanksgiving because like we come back and it's typically just 1 week of school after Thanksgiving almost every year. So like you have a week and then finals and then all right. Let's see here.
I'm being so confused as to why Thanksgiving break on 4 days long before I got here. And
Sure.
then I realized, oh, there's only like 2 weeks between Thanksgiving break and the end of the quarter.
Right. And we have an exceptionally long Christmas break or winter break this year. At least
Was it not usually in that long?
it's not usually quite that long because it just kind of depends. Sometimes like fall quarter started kind of atypically early this year just because of how the calendar worked. So yeah, we're ending fall quarter a little earlier than usually. Usually we're just ending more like the 13th and the 14th. So yeah, means a little bit longer than is usual. Here, let's see. Oh, I should give you all the attendance form. Should. Speaking of which, I did just update all the attendance in Canvas, so things should look fairly correct. Go, there's the attendance link, folks. Sorry, just for a moment here. It's going to do one more thing.
Finished the midterm early on Friday, and finished it like 20 minutes early, and I was walking up to turn it in, and she looked at me like I was going to ask her a question, and I had her the paper, and she looked at me like I was insane. She's like, "You're done?" I was like, "Yeah." And she was like, I just walked out. I was like,
Yeah, man. Like, should I be worried? Yeah.
"Got me doubt my abilities over here."
Right. Okay, so let's go ahead and get started. We're into, I think we have 5 classes left today, Wednesday, Monday, Wednesday, Friday of the following week. There are 5 sections left on the homework, sections 9.1, 9.2, 9.3, and then like I think like 5.6 and 6.5 or something like that. Which are all kind of not my favorite stuff. They're kind of like these odds and ends that are not super duper important, but we still need to talk about because you're going to be hearing them. So let's talk about section 9.1. Let's see how this pen goes. We're talking about expected value, variance, and standard deviation. I feel like I missed that one. So first things first, expected value is just another name for the mean or the average. All the same sort of thing. Some symbols we use for this are X bar or mu or E of X. You'll probably see, I don't know, it really depends. You'll see all of them. If you take stats, they are a little bit different in actual meaning, although calculation wise, they're still all the same thing. X bar in stats typically means your sample mean, whereas mu in stats means your actual population mean. So that is a difference between the two things, just so you're aware. That's for stats, though, not for this class specifically. Let's look at an example. Let's say we have let's say 6 people took the test. You took us. So you can these are not actual test scores because they're very sad that they are. But let's say 6 people scored a 0, a 0, 100, 100, an 80, and a 20 for 6 test scores. And we're going to find a few things. And these numbers are relatively easy just for the sake of calculating what we're going to calculate. So let's find the expected value, aka the mean or the average. So typically, and actually I'm gonna talk about this in two slightly different ways. One way to think about this expected value is to just take all the numbers, add them together, 0 plus 0 plus 100 plus 100 plus 80 plus 20, and divide by 6, which ends up being 50, or 300 divided by 6, which is 50. But here's how I actually want you to see, because this is leading us more towards the actual way of calculating expected value in general, when you don't always have a bunch of observations and we know how many there are. Sometimes we have a bunch of things and they're probabilities. So I'm going to think of this as 0 times 1/6 plus 0 times 1/6 plus 100 times 1/6 plus 100 times 1/6 plus 80 times 1/6 plus 20 times 1/6. But then I can combine the zeros and the hundreds together and say this is actually 0 times 2/6 plus 100 times 2/6 plus 80 times 1/6 plus 20 times 1/6. And although the end result is still the same, here's what I want you to see. This is, so the expected value of x. This is 0, and 2/6 is the probability that someone scored a 0, right? Because there's 6 people that took the test and 2 of them were people that scored 0. So this is I'm thinking of this as my first observation, x sub 1, times the probability of that first observation. And this is my second observation, x sub 2, times its probability. This is my third observation, x sub 3 times its probability. And my fourth observation, x sub 4 times its probability. So yes, you can certainly calculate an average by just adding up all the observations and dividing by the number of observations. But a more generalized formula is that, yeah, we should just write this down, is that the expected value of x, or the mean, is each x value times the probability of seeing that x value. Up to some last observation, some nth x value times its probability. And you might see your teacher write it in this way. The sum from I equals 1 to n of the of x sub I times the probability of x sub I. Or very generally, you add up every observation multiplied by its probability. That is how we find the expected value. Let's continue on. So there's 2 other things to calculate. So, yeah, words, let's see. So when you hear the word expected value or mean or average, you should be thinking it's a measure of the middle. Right? The mean of things in some way measures where the middle is. There are other ways of measuring the middle as well. I imagine most of you have probably heard the words median household income thrown around somewhere on the news at some point. And the median is slightly different than the mean. We'll talk about that a little bit later, but they're still both measures of the middle. But let's also talk about a couple other things we measure, which are the variance. So the variance is not a measure of the middle, it's a measure of how much variability. Or spread. How far out your data is spread. The more spread out it is, the higher the variance, the more centered around the middle, the smaller the variance. Here's how we calculate variance. So typically we write it as V of X. And in this particular example, it's going to be each observation minus the mean squared times the probability. So in general, it's going to look like this. And let's calculate it. So my first observation was 0, minus 50 was the mean. We're going to square that and we're going to multiply it by the probability of that observation. Also, if you have questions in the chat, feel free to ask them more in class. Our second and I should remember, just to write down the data again, our test scores were 0, 0, 100, 100, 20, and 80. And our mean was, or our expected value was 50. Just so we can see it all on the same page. So we get 0 minus 50 squared times 2/6 plus 100 minus 50 squared times 2/6 plus 20 minus 50 squared times 1/6 plus 80 minus 50 squared times 1/6. A couple things about this. We definitely, so the variance should be a positive number, right? You can't ever have a negative or zero. Well, you can have a zero variance. You can't have a negative because everything's getting squared. There's another way of calculating this, which is worse, using absolute value. We don't do that. We like to avoid absolute value function whenever we can. So we just square things and make it nice. If we calculate this, it ends up being something kind of gross. Let's see, we've got 2,500 times 2/6 plus another 2,500 times 2/6. 20 minus 50 is 30, so you got a 900 times 1/6 and another 900 times 1/6. This ends up being, let's see, 5,000, 5,000, 10,000 plus 900 plus 11,800 divided by 6, which is close to 1,967. From a statistics point of view, variance is fine, but it's not great because the units are essentially your original unit squared. So if you're measuring something like in feet, then variance would be measured in feet squared. If you average a whole bunch of things and the units were, I don't know, I'm thinking lengths for some reason. Here, like your units here don't really make a lot of sense, right? Because you're like test scores squared is not really a unit, so it's not a big deal. But still, it's kind of a big number. It's usually the longevity. What we usually do is we take the variance and then we find the standard deviation. And the standard deviation is a straightforward, very easy calculation once you know the variance. The standard deviation is just, usually write it as sigma, lowercase sigma, not uppercase sigma, lowercase sigma. It's the square root of the variance. That's all it is. So in this case, our standard deviation is approximately the square root of 1,967, which is approximately 44.3. This number here is also a measure of our variability or a spread. Specifically, it represents how far each test score is from the mean mu on average. So just a reminder of what we had. Our test scores were 0, 0, 100, 100, 20, and 80. Our mean was 50. And the standard deviation being 44.3 means on average, each test score is on average 44.3 away from the mean of 50. It's not a great way of saying it, but it's kind of the only way we really can say it. It's better thought of as just a measure of how far away from the mean might you be. A couple things here. So as far as calculating variance, we got the same sort of idea here. Instead of it being the sum of each thing multiplied by its probability, the variance here is equal to, well, let's see, I've got the x sub 1 minus the mean squared times the probability of x sub 1 plus x sub 2 minus the mean squared times the probability of x sub 2 plus, basically it's each observation minus the mean squared to make it positive times the probability. Where your observation minus the mean is kind of telling you how far away from the mean you are, and then squaring it makes it positive, so we're not adding like positive and negative. Because if you didn't square each of these things and you add this all up, it add up to 0, which is not a useful thing to know. And then, yeah, we multiply the probability by the probabilities, kind of weight it. Let's see here. Yep. Yeah, so just like the mean or the expected value can be calculated this way, let's write it out here. Expected value is the sum from I equals 1 to n of the x sub i's times the probability of x sub I the variance is the sum of all of the x sub I minus the mean squared times that probability. And the standard deviation is the square root of the variance. Questions so far about any of these things we have said? They're mostly pretty straightforward calculations. Yeah. One thing about expected value, which I think is interesting, is your expected value for like a real life situation could be a number that's not actually possible. My favorite example of this is rolling a die, specifically a 6-sided die. So let's say we roll one 6-sided die. And just in general, if you're talking about rolling dice in class, if your teacher doesn't say anything, the assumption is it's a 6-sided die. There, of course, are other number of sided dice, and if your teacher says something about those, totally fine. But they will generally assume you're using a 6-sided die if they don't say something else. So if we roll one 6-sided die, what's the expected value? Well, each side has an equal probability of 1/6. So one side has so what's the expected value of our roll, right? So the first side has 1 pip. That's what the dots on the die are called. They're called pips. Times 1/6. Plus the second side has 2 pips, probability of 1/6. Third side has 3 pips, probability of 1/6. 4 times probability of 1/6. 5 times probability of 1/6. 6 times probability of 1/6. If we add those all up together, 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21 divided by 6, which is 7 divided by 2, which is 3.5. So when you roll a die, the expected value is 3.5, which you can never actually roll. But it just means that over time, if you kept rolling a die over and over and over and over and over again, and you averaged all your results, it would tend towards this number. With the great, if you have more rolls, you'll obviously get closer to it, right? If you just do a couple rolls, you might not be close to it at all. But if you do a lot of rolls, you're going to get closer to it. So let's talk about some discrete probability. We do definitely differentiate between discrete and continuous. When you think of discrete, you should think of something, typically something that you can kind of count, for lack of a better term. So like I would say shoe size is discrete because I can wear like a 6, a 6.5, a 7, a 7.5, but there aren't like an infinite number of possibilities in between. Whereas foot length is continuous. You can have a foot length of any measure from, I don't know, 20 centimeters to shack size, right? But you can literally get any size length in between. There aren't just like, there's not like a finite number of spots where we pick. Now, well, no, I won't get too into it because it's not that important. Well, let's look at some other discrete things. Let's say a fair coin is tossed 4 times. We're going to let X equal the number of heads that come up. Let's start by listing the sample space. So the sample space is the set of all possible things that can happen. It might be useful to think of either the flips being ordered or having 4 coins of different colors so we kind of differentiate between what's happening. I think ordering is fine. So let's list the sample space. Well, oh gosh, there's a word I'm looking for. Let's separate it into different cases by how many heads we get. So if I'm going to get X equal to 0 heads, I had to have flipped tail, then tail, then tail, then tail. Right? There's no other way I can get 0 heads. But I could also get 1 head. So to get one head, I could either flip a head first and then 3 tails, or a tail first and then a head and then 2 tails, or a tail, then a tail, then a head, then a tail, or 3 tails and then a head on the last one. 2 heads. This is where it starts to get a little bit dicey here. So I can either flip 2 tails, then 2 heads, or a tail and then a head and then a tail and then a head, or then a tail and a head and a head, then a tail, or a tail and then a, sorry, brain. Sure. Am I out of tails first? I think I might be out of tails first. Sorry, a head first and then a tail and a head first, a tail and a head and a tail, or a head and a head and a tail and a tail. It's good to be systematic about this. I feel like I wasn't super systematic here. I started with tail, tail, and then I was not very super systematic. And then finally, if you want 3 heads, here's what I want you to observe. The number of ways of getting 3 heads is the same as the number of getting ways of 3 tails. I'm just taking my list for 1 head and kind of interchanging the heads and tails. So instead of head, tail, 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 I'm going to do tail, head, head, head. And here I'm going to change this to head, tail, head, head. And then head, head, tail, head. And then head, 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 tail. There's this very nice symmetry between getting the number of things you want versus the number of things you don't want. I could think of flipping 1 head, or I should say flipping 3 heads is the same as flipping 1 tail. And just like there's 4 ways of flipping 1 head, there are 4 ways of flipping 1 tail. Finally, 4 heads, there's only 1 way of getting that: head, 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 head. So this list here, which I don't want to write again, but this list of 16 things is the number, or is all the things that would be in my sample space. So my sample space is all of this. Yeah.
Why do you have 2 heads or 2 tails in that next person?
Because I might have blown it. Yeah, because I was saying a thing and doing a different thing. Sorry, thank you. There we go. Tails, head, head, head. Head, tail, head, 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 tail, head. Yes, thank you. Good call. So we have 16 things. Also, I should point out, we knew we were going to have 16, or we could have known we were going to have 16, because if you think about having 4 slots for each flip, your first flip, there are 2 possibilities. Your second flip, there are 2 possibilities. Your third flip, there are 2 possibilities. And your fourth flip, there are 2 possibilities. And 2 times 2 times 2 times 2 is 16 total possibilities. Okay. So let's make a table. So we're going to make a probability distribution table. All this table is the things that can happen, or I should say the values of our variable and their probabilities. So we called our variable x, and x is equal to the number of heads. So flipping 4 coins, you can either get 0 heads, 1 head, 2 heads, 3 heads, or 4 heads. So we're going to make our table. I'm going to say I have x and the probability of x. And the values x can take on, we just said, were 0, 1, 2, 3, or 4. And the probabilities, well, here's the great thing about probability. It's kind of most of us have a somewhat natural understanding of the probability. Like if you flip a coin, there are 2 possible outcomes. Each one is equally likely. So the probability of a head is 1/2. The probability of a tail is 1/2. Or more generally, the way you calculate the probability of anything is it's typically the number of ways for that thing to happen divided by the total number of ways anything can happen. So if I go back to rolling a die for a second, I could ask, what's the probability of rolling a 5 or greater? Well, if I'm rolling a 5 or greater, how many ways are there of doing that if I'm rolling a 6-sided die? Right, there's 2 ways of doing that. So the probability is going to be 2 ways of getting what I want divided by 6 total things that can happen, which is 2/6 reduces to 1/3. It's not that it's hard to calculate. I'm just trying to illustrate that that's how we think about probability. That is the number of ways of getting what you want divided by the total number of possible outcomes that are achievable. Okay, so here I'm thinking about the probability, this probability distribution table. The number of ways of getting 0 heads, well, it's 1 out of 16 total possible outcomes. And the probability of getting 1 head is 4 out of 16 possible outcomes. Can you see that? No, you can't. All right. And the probability of getting 2 heads is 1, 2, 3, 4, 5, 6 out of 16 possible outcomes. Probability of 3 heads is 4 out of 16. Probability of 4 heads is 1 out of 16. Definitely worth observing here 2 important things about these probabilities. Thing 1, each probability is non-negative. Is greater than or equal to 0. Can't have a negative probability. This doesn't really make sense. The other thing that's worth noting is the sum of all the probabilities is 1. Let's check that to be sure. 1/16 plus 4/16 plus 6/16 plus 4/16 plus 1/16 is 1 plus 4 plus 6 plus 4 plus 1 is 16 over 16, which is 1. And that's just really a statement that all the possible things that can happen should add up to 100% of the probability, right? It can't be more than that. You can't have more than 100% chance of things happening, but it can't be less than that. So once you know all the possible things that can happen, their probabilities have to add up to 100%, which is 1 as a decimal. And then after we have this discrete probability table, oh yeah, there's different names for this. We can ask questions like, what's the probability the number of heads is greater than or equal to 1? Well, there's a couple ways you can calculate that. You can really just add them all up. You can say, well, that's going to be the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4, which is kind of a pain to calculate. It's 4/16 plus 6/16 plus 4/16 plus 1/16, which is 4 plus 6 is 10 plus 4 plus 1 is 15/16. That's not the best way to calculate that. Not that it's not fine, but let's pretend for a second I had flipped 100 coins and I said, what's the probability that you get greater than or equal to 1 head? That's a lot of things to add up. Typically, if we're trying to find the probability that x is bigger than or equal to some number, it might make sense to calculate the complement or the leftovers. Instead, we can say that the probability that x is bigger than or equal to 1 is 1 minus the probability that x is less than 1, which in this case specifically is 1 minus the probability that x is equal to 0. X being equal to 0, the probability is 1/16. So I'm going to get 15/16. Same thing. The idea behind this is that if I add all these probabilities together, it should equal 1. So if I'm trying to calculate this part here, check this out. There's the probability that x is greater than or equal to 1. I can do that, or I can do this 1 minus this leftover bit here. Sometimes it makes more sense to do this. Sometimes it makes more sense to do that. Either way is fine. Questions? My questions. Oh yeah, there goes my water. Okay. And then, yeah, we should probably punish ourselves with this calculation. So there's a couple problems in your homework that I was looking at. Yeah, we actually have to like calculate some of this stuff. So we should do this. Yeah, we should do this. So let's calculate the standard deviation and the variance, or actually in the other order. Before either of those, the expected value and then the standard deviation and variance. So the expected value here, It's not too terrible. Let's grab our chart though. The expected value is going to be each x value multiplied by its probability added together. So we're going to get 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16. And when we add this all up, we end up with 0 plus 4/16 plus 12/16 plus 12/16 plus 4/16, which ends up being 2. Which shouldn't be super duper surprising. If you flip 4 coins, on average, you would expect that 2 of them would be heads and 2 of them would be tails. This actually speaks to a larger statistics formula where if you're doing like n things, they all have the same probability. The number of results you expect is just n times whatever that probability is. So here we're expecting 4 times 1/2 heads. Kind of cool. Not too terrible to calculate. The variance, on the other hand, is usually terrible to calculate. So here the variance is going to be the sum from I equals. I'm actually going to write that from, so I've got 1, 2, 3, 4, 5 things. So from I equals 1 to 5 of each x sub I minus the mean squared times the probability of each x sub I. So that's going to be the first x sub I, 0 minus 2 squared times the first probability, which is 1/16. I'll point out that here 0 is my x sub 1. And here, this is the probability of x sub 1. And so on. The next observation is 1 minus 2 quantity squared times 4/16. And then 2 minus 2 squared times 6/16. And then 3 minus 2 squared times 4/16 plus 4 minus 2 squared times 1/16. I should point out, I think this is problem 7 on your homework. Not that I meant for it to be, but I do think this is problem 7 on your homework. So you might not that you should pay more or less attention because of it, but if you're doing problem 7 later on, you might refer back to this, I guess. I don't imagine you have a different number of heads than I do, although I suppose you could. Just to point out here, so here the 1 is my second observation, and the 4/16 is the probability of that. The 2 is my third observation, and the probability of it is 6/16. The 3 is my fourth observation, and its probability is 4/16. And the 4 is my fifth observation. Probability 4/16. Okay, now we just try to be as reasonable as we can when calculating this. Let's see, 4 times 1/16. 1 minus 2 squared is 1 times 4/16. 0 times anything is 0. 1 times 4/16. Wow. And then finally 4 times 1/16. A lot of 4/16. There's a lot of symmetry when you flip heads. So when you do a coin flipping problem, you shouldn't be surprised to see something like this. This ends up being 1, which is not terrible. And then my standard deviation is the square root of the variance, which is the square root of 1, which is also 1. Kind of this particular example tends to be pretty nice because of how nice the numbers are. Let's look at another example. Yeah, we got time. Yeah, we got time. And then we'll probably start talking about continuous because that's where really things get interesting. Oh, I stopped sharing my screen for some reason. I did not mean to do that. I don't know how I did that. That was impressive. Sorry about that. We all can see the screen now. Here's the attendance form just to make sure everybody got it. Cool. So yeah, I like these kind of questions. This is kind of fun. Suppose a game is made in which the player receives $5 for flipping 3 heads out of 3 coins or 3 tails. but loses $2 for any other flip. So 2 heads, 1 tail, 2 tails, 1 head. Is this game, well, I don't like this question so much. Is this game fair? The question I would really ask is, should I play this game if I'm the player? Should I play? So when we ask if a game is fair, what we really mean is the expected value of my winnings $0? That's a fair game where neither player is expected to do better than the other, whether you're the player who's playing or the player who's acting as the bank or the house. So the question when we're asking is it fair is, well, I guess we have to define what we're talking about first. So let's say that X equals the amount of money that we win. And the expected value of X, well, there's two things that can happen. I can either win $5 with some probability, which I haven't calculated yet, or I can lose $2. Now, here's the thing. If I'm talking about X being the amount of money I win, then if I'm losing $2, I should say that I'm winning -$2. All right, let's talk probabilities. Let's write out our sample space. So sample space for what can happen, not for how much money I win, because we kind of already talked about that. So if I'm flipping 3 coins, I can either get 3 tails or 2 tails and 1 head. But there's more than one way of getting that. I can get first tail, then second tail, then head, or I can get tail, head, tail, or head, tail, tail. Similarly, if I get 2 heads, I can get head, head, tail, head, tail, head, tail, head, head. Finally, 3 heads would be head, head, head. So let me ask you all to think about or write down on your own what the probability of winning $5 would be, meaning what's the probability of flipping 3 heads or 3 tails? Not meant to be super complicated. Let's see. There are 1, 2 ways I can win $5 out of 8 possible things that can happen. So the probability of winning $5 is going to be 2 out of 8. And then the other thing that can happen is I can lose $2, and that's going to happen 6 out of 8 times. And yes, we could reduce those fractions, but it's not that important. So now the expected value is going to be each thing that can happen times its probability. So let's see, x1 is 5 times 2 eighths, plus x2 is -2 times 6 eighths. And it looks like that's going to be 10 eighths minus 12 eighths, which is -2 eighths, which is -1/4, or -0.25. So what does that mean? It means my expected winnings per game is -25 cents, or $-0.25, which means it's not a fair game because the expected value is 0. And more importantly, I shouldn't play it because on average, I'm expecting to lose a quarter every time I play. That's not going to happen every time, right? I might win $5 the first time, win $5 the second time, and then lose a bunch of times. But anything can happen. But on average, if I play this for a long amount of time, I'm going to expect to lose a quarter on every game. So if I play 20 games, I'm going to expect to lose $5 on average. It's kind of funny when you think about this. I think like the other, what was it, a few weeks ago when the lottery was at $2 billion, the expected value of that lottery was actually probably positive, because the probability of winning the lottery, I think, is somewhere in the hundreds of millions, like 1 out of 100 million or 500 million, something like that. So that lottery actually, from a mathematical standpoint, assuming the taxes are not like terrible, made sense to play. The expected value was probably positive. even though it didn't really make sense. But like, it's kind of interesting what the math can tell us sometimes. Let's look at one more example of this. Again, just to point out, these tables, the probabilities in them should always add up to 1. And each individual probability should always be greater than or equal to 0. Typically, they're strictly greater than 0 because it doesn't really make sense to list something whose probability is actually 0, because like, why would you care about that? But that's not always the case. Sometimes we list things that have a probability of 0, even though it seems weird. We have one more example of this discrete probability stuff. Insurance. Oh, there is something else I should show you guys. So insurance claims and their probabilities are shown in the table below. So I'll write in a second. What annual premium should the insurance company charge so that it breaks even? And this is a very kind of simplified version of what actually happens in insurance companies, right? They really do think about how much each member is going to cost them and kind of make their calculation of what premiums cost based on their projections on how much people are going to cost. So let's say that X is the amount of claim. So X could be $0 or $1,000. I was just making up some kind of very generic numbers. $5,000 or $10,000. And the probability that in a year someone has a claim that's $0 is 0.936. Someone has a claim that's $1,000 is 0.040, $5,000 is 0.020, and $10,000 is 0.004. So let's find what the expected claim per insured is. So the expected value of X, the expected value of a claim, the expected value of the claims for an insured is going to be, I mean, we can do the calculation. It's very straightforward. 0 times 0.936 plus 1,000 times 0.04 plus 5,000 times 0.02 plus 10,000 times 0.004. Adding this all up, you get 0 plus 40 plus 100 plus, I think that's another 40. Yeah. And to be $180. So on average, each insured is going to claim $180 worth of liability. So we should be charging $180 per customer, if our goal is just to break even. Which actually in some ways is not an untrue goal. Some insurance companies are actually, the insurance company my wife works for, USAA, they were started as a co-op. And so they really do, like, they take the money that they get, and if they've overcharged people, they do give it back to their members at the end of the year. Like, it's kind of, I mean, like, they're also certainly making money, but like, there's this whole kind of thing where they are member driven. It's just kind of interesting that some insurance companies actually do operate in a, we are trying to quote unquote break even. That's the goal. So let me, we won't get into the continuous stuff yet, but there is one calculation I should show you because it's going to come back up later. So I'm going to remind you all a couple times that the expected value of something is indeed the sum of each observation multiplied by its probability. And we've already seen that the variance is the sum of each observation minus whatever the mean or the expected value, but we like to write the mean because it's easier to write, squared times the probability is. So I'm going to show you an alternate way of calculating this because it's going to be super useful when we start doing this for continuous stuff. You don't really need to know this derivation, but it's nice to kind of see it so you can believe it. So you don't need to copy this down, although you're certainly welcome to. I'm going to show you how to get from this to an alternative version of this formula. So here we go. We're going to say that this, the sum of xi minus the mean squared times the probability of x sub I. And we're saying we're going from like I equals 1 to n. I just don't want to write that every time, but we certainly could. Right, so we're doing, x1 times p of x1 plus x2 times p of x2 plus x3 times p of x3, all the way to xn times p of xn. So check this out. When we write this one out, I'm going to multiply out this xi minus mu squared. So I'm going to get the sum of xi squared minus 2xi times the mean plus the mean squared times the probability of x sub I. Just doing, a minus b squared is a squared minus 2ab plus b squared. And then we're going to distribute this to each of these three terms. So we're going to write this as the sum of xi squared times the probability of x sub I minus 2xi times mu times the probability of x sub I plus mu squared times the probability of x sub I. I know it's getting a little bit unwieldy, so we're actually going to break this up into three pieces. So I don't know how much we've talked about summation, but it is true that if you're taking the sum of something minus something else or plus something else, you can think of it as the sum of the first pieces minus or plus the sum of the other pieces. Meaning we can break this up into the sum of xi squared times the probability of x sub I minus the sum of 2 times x sub I times the, oops, I forgot the mean there, I'll have to get it at the end, times the probability of x sub I times the mean. Sorry, that's kind of out of order there. Plus the sum of the mean squared times the probability of x sub I. Okay, here I am going to throw back in the i's because I need them. Kind of. I equals 1 to n, I equals 1 to n, I equals 1 to n. What I really want you to see here is that this here, right, this sum, for example, this sum from I equals 1 to n of 2 times x sub I times p of x sub I times the mean, it looks like the following, and especially don't write this part down, I think. So if I equals 1, I'm going to get like 2 times x sub 1 times p of x sub 1 times the mean. And if I is 2, I'm going to get 2 times x sub 2 times p of x sub 2 times the mean. And if I is 3, I'm going to get 2 times x sub 3 times p of x sub 3 times the mean. All the way to the last term being 2 times x sub n times p of x sub n times the mean. Now let me ask you two. I know there's only two here, but you can tell me. From each of these 1, 2, 3, 4, all the way to n terms, what can I factor out from each of those terms? A 2 for sure, and what else? Also a mu. A mu is just some number we've calculated. So you can totally write this as 2 mu times x1 times p of x1 plus x2 times p of x2 plus all the way to x sub n times p of xn. Or in other words, you can write this as 2 mu times the sum from I equals 1 to n of x sub I times p of xi. Or more generally, whenever you're dealing with summations like this, anything that doesn't have an I in it, whatever that subscript is like a constant. And so it can come out in front. So here we can totally write this. Now this is where things get cool. This is going to be the sum. Here I can't bring anything out from I equals 1 to n of x sub I squared times p of x sub I. Here I can bring out the 2 and the mu. I've got 2 mu times the sum of x sub I times p of x sub I. Plus, I can also bring out the mu here. I don't know how my mu squared became a mu sub 2. I mean, I do, it's because I wrote it wrong. This mu squared can also come out for the same sort of reason. All right, now let me ask you all. I know we've just only talked about this today, but let me phrase it this way. If I sum or add up all the probabilities, what do all the probabilities have to add up to? Right. And in a similar way, we've also seen this today, it's literally on this page. what is the sum of each x sub I times its probability? It's the mean or the expected value. So this thing right here is the mean. So look at what we've got. We've got, I think I can put this in here. We've got the sum of x sub I squared times the probability of x sub I minus 2 times the mean, or 2 times the mean squared, plus the mean squared times 1. Or in other words, we've got that it's equal to the sum of x sub I squared times the p of x sub I minus the mean squared. So this variance formula, there is an alternative. You can either write the variance of x as each x sub I minus the mean, and then you square it, and then you take and multiply by the probability. Or you can do each x sub I squared times the probability, add those all together, and then after you've done that, subtract off the mean squared. And I'll tell you, it doesn't seem so bad either way when you're doing it discretely. But when you start integrating these things, it becomes much easier to integrate x squared times your function than it is to integrate x minus your mean quantity squared times your function. This is a whole extra big calculation that we really don't want to do. So this other formula is going to be a lot nicer. All right, we'll talk more about this on Wednesday. As far as Wednesday goes, I will be here in person. If you want to come in person, you are welcome to. If you want to come virtually because you want to be on campus on the Wednesday before Thanksgiving, that is totally 100% fine, as it always is. But if you want to be here in person, I will be here for you to be here with. If it's just me and everyone virtually, that's totally fine too. I will be here talking to the camera. And have a nice I'll say it again on Wednesday, but have a nice Thanksgiving. Wherever you're going to, or not going to, whether you're in town or going abroad, not abroad, far, somewhere not here. I'll be in Livermore. But I'll see you later. I should stop this. Bye.